discussing the lac operon gene regulation. I read the article, Boolean models can explain bistability in the lac operon. This is about a discrete mathematical model for the lac operon in E. coli. They concluded that their model was more efficient than the ordinary differential equation models. So that was the main idea. Before I talk about the math, it's helpful to know what operon is. An operon is a section of DNA that contains the instructions to create a certain protein. If that operon is on, that means that you can read that information and create the protein. If it's off, it means that information is blocked and you can't perform the function because you can't create that protein. So the lac operon is specifically responsible for metabolizing lactose inside E. coli, and it only works when there's no glucose present. So the operon will be on if there's no glucose and there is lactose, and it will be off if there is glucose or if there is no lactose. The paper also talks about bistability a lot, and that's the idea that this system, so the lac operon's behavior, can settle into two different steady states, so it could be on or off. And that steady state is linked to the idea of like a light switch. So if it's switched on, it will stay in that state until there's a big enough force to move it into the other state, which would be off. So to model this system, they developed two different graphs. One of them was called the wiring graph, and that's where all the vertices are the variables, and then the edges between the vertices show interactions between variables. Those interactions can be inhibitory, which means A being present prevents B, and those are shown with dots at the end of the edges. And then it could also be a promoting interaction where A being present promotes the activation of B, and that's shown by a normal arrowhead. Loops arise in this graph, and the parity of those loops is important. So the parity of the loop is defined by the product of the parity of all the edges, where an edge has a parity of -1 if it's inhibitory, or +1 if it is or otherwise. So this loop between M to B to A to R to M is positive because the product is +1 times +1 times -1 times -1. Positive feedback loops are necessary for multiple steady states to exist because the variables keep telling each other to stay active or present. And this means once the system enters a state of being on or off, it will stay there until a large enough force comes to change the state. Negative loops, on the other hand, tend to drive variables to flip their values and are associated with systems that switch states or oscillate. And that's also important to be in the model because the lac operon can switch assignment of state. The second graph is the state transition graph. It shows all mathematically possible states between all the variables assignments. This is a Boolean model, so 1 means the variable is present or active, and 0 means it's absent or inactive, depending on what the variable means. They then added edges between those possible states that are biologically motivated, and this shows all the possible ways that all the variables could be assigned. They added stochasticity into the model. This is the idea that some variables will behave with randomness instead of being deterministic. In this application, the researchers say the lac operon could reasonably be on or off if the glucose is absent, but then there's extracellular lactose at a moderate concentration, so it still needs to be metabolized. They capture this uncertainty by assigning a normal distribution to the extracellular lactose, and that means the model will give probabilities that the operon is on or off depending on the sampled lactose concentration instead of a definitive on or off if it was deterministic. After completing the model, the researchers revised and removed extraneous variables that weren't really impacting the behavior, and they also removed the biologically impossible states seen in the state transition diagram. This makes the model simpler and computationally advantageous as it's cheaper to run because there are fewer variables and possibilities. So overall, their approach, they argued their discrete mathematical model was simpler than the ordinary differential equation ones, which is computationally advantage. They also have state spaces defined in the graph, which makes deriving the steady state behavior easier, and it shows visually the attractor states and how the steady states arise. So in conclusion, this article discusses some applications to the graph concepts we learned in MA 351 and shows the behavior of the lac operon